All right, welcome everyone. My name is Mark Stooley. I am an IBM Senior Technical Staff Member and the Chief Architect for IBM Java. I'll let Vijay introduce himself.
Thanks, Mark. I'm Vijay Sundaresan, and I'm a Senior Technical Staff Member and Java Performance Architect from IBM Canada.
Great, thanks. So we're here today to talk about optimizing optimizing performance for container-based Java workloads. And we're going to start off with a very quick step one. The first thing you need to do is pick the right JVM to run your Java workloads. And one of the reasons for that is that there are many, many different metrics, performance metrics that matter for containers, and they matter differently for containers than when you're running outside a container. Also, there are some concerns and considerations that come into play when you're running containers in the cloud that are important as well. So let's dive right into this. So optimizing when you have many metrics to take into consideration requires really a balanced approach, right? When normally outside of the cloud or outside of containers, you talk about throughput or maybe CPU consumption or response times. It's a relatively simple equation. But when you're looking at containers, you really find that a lot of different metrics come into play around startup time, ramp up time, how much memory footprint is being consumed by your Java application as it runs, and so on, in addition to things like throughput. And you really have to keep a balance when you're running inside these metrics to run Java applications. And this matters really in the JVM, right? You have to make sensible trade-offs in how you design your JVM to be able to maintain a balance across all of these different metrics. Different applications are going to have different goals, and that drives different design decisions. But really, you have to take into account many, many different Java workloads in the JVM. And there's no single right answer. There's lots of use cases here, and it requires a balance. And I'm going to make the statement that optimizing for containers requires a different balance across these performance metrics. And let's talk a little bit more about where that comes in. So containers are frequently used in the cloud to run Java applications. And there are some interesting things that come into play when you're talking about the cloud. Now, everyone knows the cloud is basically a compute-on-demand system. You get a bill for the resources that you're using. Many, in fact, migrate to the cloud seeking to lower their capital or operational expenses for running their Java-based workloads. And that brings an increased focus on reducing the resource usage associated with your applications to save money. But on the flip side, another common trait when you're running in cloud and using containers is that your applications are being divided into microservices rather than existing as large monolithic applications. And that creates actually more resource consumption because now you have more JVMs that are consuming more memory and using more cycles to run your applications. On top of that, the capacity that you need to run your applications can change quite rapidly because it's on demand. You can actually scale it to meet the demands that are active at the time. That can result in more frequent deployments, which brings an increased focus on startup time. And I'll explain startup time as basically the time that you're paying for resources, but you're not actually making any money because you're not doing any work yet. Now, because it's Java, you don't actually control the resources that are being used directly by your application. It's the Java virtual machine itself that's managing those resources on your behalf. And so that's the reason why the very first important step here is to choose a JVM that has been optimized to take into account the increased focus on reducing resource usage to save money and also to focus on startup time. So which JVM are we going to recommend? We're going to recommend the Eclipse OpenJ9 Java virtual machine. It's an open source JVM. It was contributed originally by IBM in 2017. And through its long history, it's been optimized slightly differently in order to focus on memory consumption and startup time. And these are the attributes that matter a lot when you're running with containers in the cloud. Now, OpenJ9 is an open source project, so you can't actually get builds or binaries to run your applications from OpenJ9. But IBM stepped forward in the last few months to generate the IBM SEMERU RUNTIMES, which has a fairly easy link there to be able to find and get access to them. These are basically open JDK class libraries combined with the Eclipse OpenJ9 Java virtual machine to provide a very stable, secure, high performance, and cloud optimized Java runtime environment. And they're available at no cost. There's a couple of different editions which are 100% compatible with one another, the Open Edition and the Certified Edition. It's different licenses and whether it's been TCK certified or not. Let me just explain the name that we chose, the SEMERU name. It's in honor of the Mount SEMERU, which is the tallest mountain on the island of Java in Indonesia. And I like to say it's the part of Java that's in the clouds, as a homage to OpenJ9 and the performance characteristics that make it really well suited for running Java workloads in the cloud. So the much smaller footprint, much faster startup, faster time to peak performance, and all with very little impact to throughput, if any. So for the rest of the talk, we're going to be talking about Java performance in the cloud and in containers, where the backdrop of all of this is using computing resources is money. So we want to save on using computing resources. And we're going to divide the talk into 4 little sections. Small deployment size, you want to make your container small. You want to be able to recognize the resource limitations that are being imposed by the environment, like on the container itself. But even if you're aware of the limits, you don't want to necessarily use everything that you're given. You want to use those judiciously so that you don't waste resources. And finally, that fast startup problem that I mentioned is the time that you're using resources but not really getting any work done. So the theme here is keep each container small and scale out new container instances quickly. I'm going to cover the first 3 of these relatively quickly, and then I'm going to switch to VJ. He'll go through the fast startup section, which is in a little bit more depth. So the first is small deployment size, small containers. Why do you want small containers? Well, it's good for security. You shouldn't be including things in your containers that aren't being used unless there's a lower attack surface area. Also, it reduces push time for developers and pull time for your Java deployments. So it's just basically good to do. And there are some relatively easy things you can do to have to dramatically improve on the image size that you have. The first 3 recipes that we're going to recommend here are: 1, use a JRE instead of a JDK so that you can save space. The JDK has lots of tools that are great for development time, but they're not really used for deployed Java applications. The second one, if you're using Java 11 or later, you can use JLink to remove modules from your from the runtime that aren't going to be used by your application, and that can save you some space. And the third one is to pick a different or smaller base OS image for your containers so that you don't have a lot of extra stuff that might not be needed in your application to run your application. So there's a small table here that just kind of shows for one particular platform the kind of scale of numbers that you can get by applying some of these recipes. So these numbers are out of date, really, but they give you a flavor for the sort of scale of change that you can expect. So if you look at the JDK images here, the latest Ubuntu and the UBI minimal, you're looking at about 150 megabytes of container size required. If you were to switch to an Alpine image, which is a much smaller Linux image, you can get that down to 117-ish megabytes. On the flip side, if you move from JDK to JRE, you can go down to 81 megabytes. So that's saving almost half of the container size at this point. And finally, these two are not dependent in any way, so you can combine the two together. And if you use a JRE with Alpine, you get down to about 52 megabytes. So now you've reduced your container size by about 3. With relatively easy things. Now, if you're not using certain modules, you can use JLink to get that even smaller. But these first 2 changes are usually things that just about any Java application can take advantage of, whereas the JLink one is more dependent on what modules your applications are using. And they require a little bit more sort of awareness of what your application is doing. Just for reference, I've shown the commands here that you can use to get the IBM SEMERU runtimes base images that are available for Java 8, Java 11, and soon Java 17. Now, those images don't come with an Alpine variant. So how would you use a different base image if you wanted to? It's a simple process with these 5 lines of code. You can just basically name the SEMERU runtimes image as SEMERU here. The real base image that you'll use is this from Alpine. So Alpine is the example smaller base image that we're going to use. And then this copy command just basically copies the JRE directory out of the SEMERU runtimes image and into the image that you're building. And that way you can get all of the JRE functionality you require inside an Alpine-based image. So really very simple to do. And as the previous slide showed, you get a very nice benefit in terms of size by doing that. All right, let's move on to container awareness. Now, this is what the phrase that we use for being aware of the limits that are being imposed by the environment, right? When a container is deployed, it generally has limits in terms of how much memory it's allowed to use and how many processors it's allowed to use. So what's the downside if you don't have container awareness? This slide will help us understand that. So in an environment where the container limit is 1 gigabyte and it's deployed on a system, a host system that has 16 gigabytes, if the JVM isn't aware of the container limit, it's going to allocate a heap size that's way bigger than the container limit. You're going to throw out of memory, and then that's a pretty stark consequence. You're going to just die. Similarly, on the CPU side, if you have a container limit of 1 processor, but you get deployed on a large machine that has 64 processors, the JVM thinks it can use 64 processors. It's going to allocate lots of JIT compiler threads, lots of garbage collector threads. Your thread pools are going to be allocated with many, many threads initially, and you're likely going to get very, very poor performance. On top of the fact that if you've got a 1 processor container on a 64-bit 64 processor machine, there's probably 63 other containers that are in exactly the same state. So you're going to completely swamp this machine with resource requirements. And so you can have stability and performance problems if you're not aware of the container limits. And so OpenJ9, I'm happy to say, is aware of the limits in all of the active releases from Java 8+. It's active by default, in fact, now. So you don't even have to do anything to get access to this awareness. Now, there are a couple of usability things here. Some people, although I don't recommend it, some people run their Java applications inside a container without an XMX, so not specifying what the maximum heap size is. And that can really, they sort of rely on the default heuristics that the JVM uses. With OpenJ9, actually, we've modified those heuristics so that if it detects that you're running inside a container, it will increase the amount of memory that you would allocate by default if you aren't specifying a max heap. The theory here is that if you're running Java inside a container, it's probably the only thing that's running inside the container, and so it can afford to use more of those resources. However, depending on your application, you may need more memory for native allocation or want less memory for allocation. The default may not work for you. The recommended way to do this actually is with these max RAM percentage and initial RAM percentage options, which essentially just give you an ability to specify a relative heap size based on the size of the container limit. So if you have a small container, on the right side here, it will allocate a heap of, in this case, 1.6 out of 2 gigs. If you are in a large container, then it will allocate a much larger heap. And so the benefit here is that there aren't 2 places where you have to code the size of the limit or the size of the heap that you want. And if you end up deploying with a larger container limit, you don't necessarily have to go in and modify the image in order to run with a larger heap size by changing that command line option. So you can just do it with percentages. All right. Even if you are aware of the limits that you've been given, you still want to use your computing resources judiciously, right? Because they cost money when you use the resources. And in fact, the cloud is really about sharing. You're trying to pack as many things as possible onto as few resources as possible. So you don't want anybody to be greedy in that scenario because you're taking resources that other containers might be able to benefit from. OpenJ9 here is extremely conservative with its heap growth. It tries not to grow the heap unless it thinks there will be a valuable throughput benefit that you will get from growing the heap. It also frees memory that's used transiently by JIT compilation very aggressively, so that that memory consumption only shows up very, very instantaneously, and it's gone by the time that you would actually measure it. The graph here at the bottom here is showing the execution of an application called Acme Air. It's a Java EE7 application, I believe, and looking at sort of steady state memory footprint. So this is under load processing, some level of load, and how much memory it's consuming dynamically. If you can see the OpenJ9 bar, which is the blue bar, regardless of what the container limit is, the blue bar is roughly the same height. And that means that OpenJ9's resource consumption is proportional to the load that you're applying. That's the thing we're keeping constant here. There's the same load for these 3 environments. You can see that other JVMs aren't necessarily quite so aware of what's going on, and they grow to use more resources if the container limit grows, even though there probably isn't much of a benefit in terms of throughput. I didn't show it on this graph, but the throughput here is the same in all scenarios. So it's providing consistent throughput, handling the same amount of load, but using memory resources more judiciously, which means you're spending less money. All right, so at this point, I'm going to transfer over to Vijay, and he'll cover the remainder of the talk on fast startup. Go ahead, Vijay.
Thank you, Mark. Next slide. So the first topic I'll be covering under the startup umbrella, and I'll be covering 2 or 3 different areas, is class verification. So class verification happens when classes are being loaded, so early on during startup time, as you might imagine. And this is an overhead that the JVM brings in. Obviously, it takes time to verify that the bytecodes are well formed and won't cause any security issues. It is recommended that you always run with the verifier on. So what we've done in the OpenJ9 JVM is to optimize the verification process such that if the verifier itself was loading new classes, we kind of minimize that. We defer the loading of classes until the program actually runs and wants to naturally load those classes. Instead of verifying right on the spot, what we do is we keep track of what we would have done if the class had been loaded by the verifier, and instead repeat those verification operations later on in the run when the program loads that class in natural course. This option or this feature is enabled by the option that's shown at the bottom of the slide. Next slide, please. So one of the reasons why OpenJ9 has such great startup time characteristics is this technology called the shared class cache. So what is the shared class cache? Basically, it's a memory mapped file that contains the unchanging parts of classes, so like bytecodes and constant pools and things like that, and ahead of time compiled code, and sundry other pieces of information like profiling, etc., that help improve startup time. So you can imagine how storing classes inside the shared class cache would speed up class loading, for example. You don't need to repeat the same process that a JVM instance followed in populating the shared class cache. So the way the shared class cache works is a JVM instance runs, it populates the cache with all those artifacts, and then subsequent JVM instances can pull those artifacts in from the cache and avoid doing some of the computation, whether it's class loading or JIT compilation. And this is where AOT compilation comes in. So that's the bottom half of the slide. So in short, ahead of time compilation is compilation done outside of the running JVM, so that there's already an ahead of time compiled body available in the shared class cache, and a subsequent JVM just needs to pick it up and run with it. Loading up an ahead of time compiled body is 100 times faster than compiling that method. So you can see how this technology, AOT technology, can really shrink the overhead of JIT compilation during startup. Next slide, please. So these are great, shared class cache and AOT, but they have challenges when you run them in the context of containers. So in particular, the biggest problem is that a container is a very ephemeral thing. It goes away when your work is done. There's only one JVM running inside a container. So the whole shared class cache concept is around sharing with other JVM instances. And you're never going to get the chance to share with other JVM instances in a container simply because of the way containers work. So what are the alternatives? You can use volumes, but they're cumbersome, especially in a cluster of nodes, and you don't know where your pod is going to be scheduled. How can you make sure that the right shared class cache is available on the right node in the cluster? So it gets very complicated very fast. So instead, what we did was we chose to package the shared class cache inside the OpenJ9 container images themselves. So this way, what we do is when we're building the OpenJ9 container image, we start and stop a training app, and we put in a bunch of Java class library classes into the shared class cache, and we ship the container with that cache. So this way, users can benefit directly from the cache that's embedded in the image, and they don't have to suffer the cost of populating the cache themselves. The only downside is that because we're only putting in Java class library classes, you don't get the full benefit of shared class cache. You don't have your application classes included in there. Next page. So this shortcoming can be addressed, though, when you build your own container images that are based on OpenJ9. And this is where this multi-layered shared class cache technology comes in. So it allows you to add your own applications classes into the shared class cache that you put into the container image for your application. So the methodology is very similar to what the OpenJ9 build process followed, which is you have to start and stop your specific application during the Docker image creation step. And if you did that, then the shared class cache will contain classes from your application as well. Now, potential issues in this are that in order for you to be able to add your classes, the cache needs to be large enough to allow addition of these new classes to it. And this is where we made this multi-layer shared class cache to address some of the rough edges around that. If you just had a single shared class cache at the OpenJ9 layer, what we would have had to do is to increase its size to allow application classes to get in there artificially. So it would be empty most of the time, or partially full most of the time, just on the off chance that an application class could be added at a higher layer. Further, if you add an application class into the shared class cache, the way containers work is it'll make a copy of that file entirely. Even if you wanted to add a single class, the entire shared class cache would get duplicated and added to a higher layer by Docker. So the multi-layer shared class cache solves this in a couple of different ways. One, because these distinct layers are independent of each other, they can be sized independently of each other as well. You don't have to size the OpenJ9 cache to be larger just on the off chance that a higher layer may add some classes to it. The higher layer can size its own layers shared class cache appropriately. Again, because these are different files altogether, you also don't fall victim to the copy on write problem. You can add classes to the higher layer, and there's no duplicated bytes in your image as a result. Next slide, please. So the final sort of tweak we had to do to this shared class cache technology to work well in containers is this portable AOT feature. And this is a simple concept at its core. When you're running a JIT compiler, you're producing code in memory and running it. But with embedded shared class cache and embedded ahead of time compiled code in container images, basically you have a different sort of equation altogether. Now it really matters where you're building your image and where you're running that image. So if you are, for example, building your image on a newer architecture version, and you're running that image on an older architecture version, you don't want to use newer instructions in the ahead of time compiled code, because that code, when it runs on the older architecture machine, could crash. So you need to take care, or you may have had to worry about this problem, but OpenJ9 solves this problem for you nicely by generating what we call portable ahead of time compiled code. So this is a bit like statically compiled code in a sense that it compiles for the lowest architecture version that is supported. So it doesn't take advantage of the latest and greatest architecture features on the machine we're running on or building on, and this allows the code to run portably wherever whatever your runtime environment is, wherever you're running the image. Next page. So with all of these cool technologies that we talked about, let's look at some results. So on this slide, we show three graphs. On the left is startup time, middle is memory footprint, right is Docker container image size. The startup time graph first. So we're comparing against Hotspot, OpenJ9 to begin with, slightly slower running this Spring application called Pet Clinic. Then when you start optimizing for the verifier, the class relationship verifier, as I said, OpenJ9 startup time shrinks a little bit. Then when you start embedding a system SCC, so just the Java class library classes, it shrinks even that much more. And then those three bars after that are significantly lower, because now you've put application classes into the shared class cache as well in your own application layer image. And you can see there's a dramatic reduction in startup time. It's far faster than every other bar in that graph. The middle graph talks about memory footprint, and this is relatively straightforward. Just simply using OpenJ9 gives you a good memory footprint benefit. Yes, there are some minor variations there. If you're adding a shared class cache, the footprint grows a little bit. But for the most part, the OpenJ9 bars are all well below the Hotspot ones. And finally, quickly looking at the image size, OpenJ9 image starts out smaller than the Hotspot one. It grows a little bit as you put shared class cache into the embedding, as you start embedding shared class cache into the image. And as you put application classes, it grows even more. But the multi-layer shared class cache succeeds in really reducing the disk usage of the shared class cache. If you didn't have that, the bar on the extreme right is the one showing the most disk usage. So overall, yes, disk use went up or image size went up, but you also got a healthy startup time boost because of that. Okay, over to the final slide to wrap up here. In this presentation, you heard about several innovations that we've done in the OpenJ9 JVM. It make it, in our opinions, your best choice to run Java in containers. The OpenJ9 JVM is available in IBM SEMERU runtimes. The link is shown on the page there. You can also pull the Docker images using the tag shown there. We talked about optimizing for containers in many different ways: smaller deployment size, recognizing resource limits, using those resources judiciously, fast startup time, using shared class cache designed specifically for containers and addressing usability concerns there. And you get all that with a full Java implementation without any limits on which features you're using. So overall, please, we would encourage you to take a look at OpenJ9's balanced container optimization story, because at the end of the day, it could save you money. With that, I conclude the talk, and we can go on to questions now. Any questions?
Do we have questions?
So, thanks for the great talk. It's a really good and informative. So I have a question. Like you mentioned the Docker container for the Java 8 and 11. What about are you only targeting for the long-term support LTS Java versions? So you're not targeting for the 15, 16, and etc.
Right. Yeah. So we build all of the feature releases as they come out. We're currently at OpenJ9. We're currently focused on getting Java 17 out the door right now. It's in its ramp down phase right now, so it should be out shortly. And we've already got people who are already focused at looking at what's coming in Java 18 and what's going to be coming in future releases. We basically follow the same release model that everyone else in the Java community follows. So we support feature releases for 6 months, the 6-month period after they come out, and LTS releases are the ones that are long-term supported and the ones that IBM SEMERU Runtimes provides a sort of longer support for.
Great, thank you. So the other question is, it's kind of in Java, is the kind of now is a GraalVM, the build time compilation, and then OpenJ9 focus on the AOT. Can you tell me the differences? Why do you think AOT is kind of the way forward for OpenJ9? Do you think OpenJ9 is kind of will also adopt some features from GraalVM?
Well, the main reason or the main difference between Graal native images and what OpenJ9 has in terms of AOT technology is that it's lesser of an opt-in step. It's more natural to fit into the application that you have. The Graal native image requires you to adhere to a set of constraints that it imposes on your application, whereas with the AOT technology, it's basically transparent to you. All you have to do is just add shared classes to your command line, and it just works. So no restrictions on what's in your application, what you're allowed to do and what you're not allowed to do, etc. So it's a trade-off. If you really are looking for that super fast startup time, you have to do work to opt into those constraints, and you get it. Otherwise, any Java application out there can run and take advantage of OpenJ9's excellent startup time story, and it is quite a substantial improvement over what Hotspot can produce at this time. Mark,
it's also a better sustained performance story in terms of throughput and memory footprint under load. I would say is a better story than so. Yes, it's fast startup with native images, but the sort of sustained steady state performance equation isn't quite as attractive. So if you really care about startup, then it's great.
Right. So the other thing that I want to say is with AOT, at least for the debug purpose and for the monitoring aspect.
Right.
So you still have a lot of tooling support for that.
Yeah, all the same tools that Java developers are used to.
Yeah, great. So.
All right. Thanks, everyone. Bye.
Thank you, everyone. Bye-bye.